In this video, we're going to introduce Chem Activity 14A, looking at the E1 elimination reaction. Now, as we know, alkyl halides can undergo substitution reactions with appropriate nucleophiles under appropriate conditions. Those same alkyl halides can undergo elimination reactions under sometimes similar conditions. Substitution reactions happen through one of two mechanisms, SN1 or SN2, and likewise elimination reactions can happen through one of three possible mechanisms. Now remember, Chapter 8, we learned about addition reactions. That is, if you have an alkene and an XY, an appropriate XY, you'll make two new sigma bonds replacing the pi bond. We also, in that chapter, introduced the fact that if you lose X and Y from adjacent atoms, you can get an alkene. This is an example of an elimination reaction. In the current chapter, we're going to be focusing on elimination reactions in which there is a leaving group, such as our halide, and next to it a hydrogen to give our alkene product. If the H and the leaving group both leave and put a pi bond between them, we get an elimination reaction. Now, part of the terminology for this is referring to the two carbon atoms that are going to make the pi bond. The carbon atom in which the leaving group occurs is called the alpha carbon atom, and the carbon atom in which the hydrogen is attached is the beta atom, and the alpha and beta carbons must be attached to each other. So let's look at a real example. Here we have an alkyl bromide, a tertiary alkyl bromide, and if we redraw it, we can see that it actually has 1, 2, 3 different beta carbons, all of which are different from each other and all of which have hydrogens on them. Any one of these beta hydrogens can be lost during the E1 elimination. Say, for example, the position that I've numbered 2 here. If the leaving group left from the central carbon atom and the hydrogen left from the carbon 2, we would end up with an alkene as shown. On the other hand, if we were to lose the bromide and lose a hydrogen from the beta carbon labeled 3, we would create a different alkene that in fact has both E and Z forms. And if we were to lose the hydrogen from beta carbon 1, we would make yet a different set of E and Z products. In elimination reactions, all possible alkenes are formed, but not in equal amounts. To determine the major products of the reactions, you need to understand Zaisev's rule, which says that the most stable alkene is formed in greatest amounts. So if we look carefully at our alkenes, the first alkene is a so-called di-substituted alkene. There are 2 bonds to carbon to the 2 sp2 hybridized carbons. The second and third alkenes are both tri-substituted alkenes. That is, if you look at the 2 sp2 carbons, there are 3 additional carbon atoms involved. The second and third products in both E and Z forms are more stable than the first product and would be formed in greater amounts in this reaction. Finally, we're going to look at the E1 mechanism, specifically for the first product shown on the previous slide. E1 mechanism, it actually starts out the same way as the SN1 mechanism, where the 1 indicates a unimolecular reaction. And just like the SN1 reaction, the first step in E1 elimination is the carbon leaving group bond breaks, with the leaving group taking its electrons with it. It leaves behind a carbocation, and just like with the SN1 mechanism, things that stabilize the carbocation would tend to favor this reaction. In the example given, a tertiary carbocation is formed. In the second step of the E1 elimination, a base in solution, which may or may not be the leaving group you kicked out, grabs on to the beta hydrogen, and the beta hydrogen leaves behind its pair of electrons. This creates the new CC pi bond that we see and tells us why a base must be present for an E1 elimination to take place. Overall, the E1 elimination mechanism is or at least a 2-step reaction, in which the first step is highly endothermic because a bond is broken and not made, and the second step is highly exothermic because a bond is made. The first step is the slow or rate determining step, and it is the same rate determining step and therefore has the same rate factors as the SN1 reaction.